Welcome to The Explainer. I am so incredibly excited to jump into this with you today because we're going to explore one of the absolute most dramatic stories in the entire universe, the life cycle of stars. Now, this isn't just a simple timeline. It's a tale completely dictated by one single powerful trait, a star's mass. That one characteristic determines a lifespan that can span anywhere from a blazing, fast-paced few million years to a slow, steady burn lasting for trillions of years. Okay, let's dive into this roadmap. We'll start out in the cosmic nursery, hit the main sequence, look at the ticking clock of mass, and then see how the paths wildly split between sun-like stars and massive stars before wrapping everything up in the stellar graveyard. All right, Section 1, the cosmic nursery. To really get how this all works, we've got to head out into the deep, dark, freezing vastness of space, long before there's any light or heat at all. Every single star in the universe starts right here, in a stellar nebula. It's just a giant, sprawling cloud of gas, mostly hydrogen, and dust. And what actually wakes this dormant cloud up? Gravity. Slowly but surely, it pulls on the cloud, causing all that material to start collapsing inward and clumping together. As gravity just keeps on pulling, drawing more and more material right into the center of this clump, things start to change dramatically. The center gets way denser and immensely hotter. This sheer gravitational collapse creates intense building pressure and heat right at the core. And that extreme environment, that births what we call a protostar. It's essentially the swirling heating precursor to a true star. Now, what's really interesting about this slide is this exact number, 15 million degrees Celsius. That temperature isn't just a random milestone, it is the ultimate tipping point. I mean, it's hotter than the center of our own sun right now. It's the precise threshold where the heat and pressure inside the protostar's core becomes so extreme that hydrogen atoms are literally forced to fuse together into helium. Nuclear fusion has officially begun. Boom! With that nuclear fusion comes this tremendous, massive release of outward energy that finally pushes back against the crushing weight of gravity. In that brilliant flash of light and heat, a star is officially born. Moving right along to Section 2, the main sequence. So, as you can see, every star takes this exact same shared journey early on. They all begin in the stellar nebula, they condense down into a protostar, and once fusion ignites, they land proudly on Step 3, the main sequence phase. Now, this phase is defined by one key trait. It is the longest and absolutely most stable phase of its life. To put this into a perspective we can easily grasp, our very own sun is currently hanging out right in the middle of this exact stage. Every single day you feel the warmth on your face, you are literally experiencing the steady, stable, hydrogen-burning power of a main sequence star. But here's the catch. Section 3, the ticking clock of mass. That stable burning of hydrogen fuel, it cannot last forever. There's a finite amount of fuel in that core, and the clock is ticking from the exact moment the star is born. Which leads us to a pretty critical question. What happens when the core runs out of fuel? Well, when the hydrogen is finally exhausted, the outward pressure of fusion just stops, and gravity begins to win the cosmic arm wrestle. From this exact moment forward, the star's life path is forced to radically diverge. So the crucial point is mass. Everything moving forward splits into two totally distinct paths, low to medium mass stars versus high mass stars. Mass is the single variable that decides if a star is going to gently fade away into the cosmic night or if it's going to go out with an apocalyptic bang. Let's look at the little guys first. Section 4, Fates of Sun-like Stars. The demise of a sun-like star is relatively peaceful. Without hydrogen, the core shrinks, but the outer layers actually expand outward, eventually swelling up so large it would swallow the orbits of the inner planets if it were our sun. It becomes a massive red giant. Inside, it actually manages to fuse helium into slightly heavier elements, like carbon. But eventually, it just can't hold on. It gently ejects its outer layers deep into space, leaving behind a beautifully delicate, glowing shell of gas that we call a planetary nebula. Let's move to and see how this builds for the heavyweights. Section 5, Fates of Massive Stars. Now, a high-mass star doesn't just become a giant, it swells into a terrifying red supergiant. Because of its sheer immense gravity, when it runs out of hydrogen and then helium, it just keeps squeezing. It violently fuses heavier and heavier elements in a desperate attempt to survive gravity's crush. It fuses neon, then oxygen, then silicon, until finally it creates a core made entirely of iron. But here's the problem. Iron is a total thermodynamic trap. Fusing iron actually requires more energy than it releases. It doesn't produce the outward pressure needed to power the star. Instead, it drains the star's energy. It completely breaks the delicate balance against gravity, dooming the star in literally a fraction of a second. With nothing pushing back anymore, gravity utterly crushes the star. The core collapses in on itself with such unimaginable force that it rebounds, violently blasting the rest of the star across the universe in a breathtaking, cataclysmic explosion. This is the supernova, and it can briefly outshine an entire galaxy. Which brings us to the end of the line. Section 6, the stellar graveyard. Let's compare the remnants left behind. For our low-mass sun-like stars, only the incredibly hot, dense core remains, a white dwarf. Over billions of years, it slowly loses its heat, eventually cooling down to become a dark, silent black dwarf. But for high-mass stars, the results are totally mind-bending. A surviving core between 1.4 and 3 times our sun's mass crushes down into a neutron star. We're talking so incredibly dense that a single teaspoon of it would weigh 1 billion tons on Earth. And if that surviving core is more than 3 times the sun's mass, gravity entirely collapses the core completely out of our observable universe, forming a black hole. And this brilliantly illustrates the entire journey right here. Notice how both paths start out perfectly identical, a stellar nebula condensing into a protostar and burning steadily on the main sequence. But watch how they radically diverge later. The low-mass star gently fades from a red giant to a planetary nebula, ending as a white dwarf, while the high-mass star ramps up from a red supergiant to a violent supernova, leaving behind a neutron star or a black hole. It is just an incredibly elegant summary of how mass dictates destiny. So, I'll leave you with this provocative thought. Which massive star currently shining up there in our night sky is secretly sitting on an iron core, ticking down to a brilliant supernova right now? Thank you so much for joining me for this explainer. I really hope this journey helped illuminate the life cycle of stars for you. Next time you look up at the night sky, you won't just see twinkling lights. You'll see massive stellar engines at every stage of life and death. Keep looking up, keep asking questions, and I'll see you in the next one.